On 30 May 2022 I published a circuit on YouTube, and it was a 3 transistor beeper, and here is the schematic again. I tried to make a somewhat other circuit with this more or less classic setup of an oscillator, an NPN transistor, PNP transistor, back coupling capacitor, so there is a time dependent element in the whole oscillator unit, and this transistor only serves as a kind of amplifier. Of course, in the most primitive way, all these circuits on, say, approximately 1.5 volt, 3 volt, perhaps even 5 volt, without any, say, kind of good stabilizing of the end transistor power audio amplifier, they are somewhat critical. But anyway, I made today another circuit, and that's here in its experimental stage on the breadboard. Like I told, I did more experiments and found something very peculiar. I want to show it. So that's the first thing, because I found that a reverse transistor can work. And of course I know that there are many articles in electronic magazines where this issue is extensively discussed. So when you mount an NPN transistor instead of a PNP transistor, in some cases, and that's very peculiar, it can work, but of course not work properly. In many cases there are problems, especially when a current has to be driven. In such a case, a reversed transistor doesn't work properly, but I know magazines of the 1980s or perhaps 1990s in the Netherlands, a lecture where this issue was discussed very properly. So perhaps you can find, at least when you live in the Netherlands and you can read Dutch, these articles again. Want to focus now on only this circuit, and here is that reverse transistor. I've tested it over and over, tried to use here, say, try to reverse that transistor in a proper way, because we know that a PNP transistor needs a positive on its emitter, and now it has, well, yes, a positive on its emitter, and now it has a negative on its emitter. But I tested it over and over and it worked, etc, etc. So I want to publish the circuit as it is, and I'm also very interested in all kinds of experimental results. Here are the pin connections of the used transistors: BD139 NPN, BD140 PNP. Is here the BD140 PNP. It's in fact reversed, so we cannot amplify, but on the other hand, I try to omit it, try to use another configuration, and it all did not work. But this worked, and the good thing of it all is that it works on 1.5 volts. That's also very interesting. Often these circuits don't work on such a low voltage, and then I mean with standard silicon transistors, because the barrier voltage of a standard silicon transistor is approximately 0.7 up to 0.8 volts, and the difference between that barrier voltage and the supply voltage is in many cases too low to make a circuit work, but it works. I want to demonstrate that it's a beeper, and I can go, say, to high frequencies. I also want to demonstrate that. I only have here now one Panasonic 1.5 volt battery. And you surely can hear the sound. And you can set the frequency here. Here with that potentiometer here. And when you hear this, you are more or less sure that you can go to ultrasound, and then I mean especially all frequencies higher than 18 kilocycles, say up to 30 kilocycles or perhaps 50 kilocycles, etc. But of course, the oscilloscope is in fact the only instrument that can tell us more about the properties of this circuit. So let's look on the scope. The good thing of this scope is that it also has a frequency counter integrated. So again, the voltage supplied, and this is the waveform. Frequency is 108 Hertz approximately. Now I turn that potentiometer of 220K. I don't know where it comes from, but oh, I have to say, give the scope a new start. So this is 1.7 kilohertz. I now will go higher. This is my hand, effect of my hand. So, and you can even go on a 1.5 volt battery to these high frequencies. And that's, I think, a very good thing to tell. I have to lift up the amplification of the scope. And I'm gonna push the auto set again to see where the scope brings me. And it's 14 kilohertz, a strange waveform. That doesn't matter much, in my opinion. Well, and when I turn that potentiometer somewhat higher, perhaps we can go to higher frequencies, and this is the potentiometer on its maximum. So this is the maximum frequency that this circuit can bring on 1.5 volts, and I think that's extremely good. The scope is not able at the moment to detect the exact frequency, but there is a frequency sent out. So, and here you can see where it goes to, say approximately 20 kilohertz. So that's in effect very good. That was one part of what I wanted to tell. Perhaps I can go to the other part. Wanted to demonstrate the difference of efficiency about a tweeter. This is a tweeter that's specially made for high frequencies, going from 12 kilohertz up to approximately 25 kilohertz, and this is a normal audio loudspeaker. And the efficiency of this tweeter is much higher compared to this standard normal audio loudspeaker. It can go up to, at least in theory and also in practice, approximately to 7 kilohertz, 8 kilohertz, perhaps 10 kilohertz. it's not made to reproduce high frequencies, and this tweeter is made to reproduce high frequencies with a very good efficiency. So we have here a so-called dome tweeter. The dome is very light, and that means that it can follow the electromagnetic influences very properly, especially on higher frequencies, say around 15 kilohertz up to 22 kilohertz. And you can also see it's a very, very big magnet here. That is also to do with the say the properties of a tweeter. The magnet makes also that this dome coil, light dome coil, especially made for high frequencies, can move in a very quick way. And here we have, say, of course also a quite good magnet, but not specially made for these high frequencies. And that also means that when you connect, for instance, this speaker instead of this speaker, you hear the sound much more faint. And perhaps I can try it. Hope it will succeed. And of course I have to go to a lower frequency, but anyway. Well, you can hear it now. You can also see on the scope the frequency that's now generated. 100 Hertz approximately is sent out to this simple loudspeaker. Anyway, let's listen. And you can directly hear that the efficiency of this mini loudspeaker is not so good, but interesting to tell that where our ears are more sensitive, that's in the range from say 1 kilohertz up to approximately 4 kilohertz, the sound is heard much better. So and it even is able to reproduce that high frequency, but of course we can't hear it, and that is also everything to do with perhaps how YouTube remakes the uploads. Anyway, I've talked earlier about it. Well, this was more or less all to tell. Most interesting thing is, in my opinion, that we have here that reverse transistor. And again, that's very, very strange. It works. Most important thing to tell here is that resistor, I thought resistor, but I mean transistor. So the PNP transistor is mounted in a reversed way, and it adds something to the circuit. At least it makes the circuit work. So when you are interested, here is a more or less practical schematic. So you can solder this or not solder this, or make it on a breadboard, and I'm very interested about the results. And important to tell, a ceramic tweeter doesn't work. The impedance is too high, so you need a real loudspeaker with an ohms resistance in the range of 4 to 8 ohms. Pen over somewhat, and I'm now approximately on the maximum time that my camera can make and bring. Thanks for watching.